Okay. So before we begin, I just want to read a quick land acknowledgement. So the Southern California Bight, where we conduct most of our work here at USCC Grant, is located on the unceded sacred and traditional lands of the Tongva, Ajashaman, and Chumash nations. They're the first native peoples, and they are the original stewards of this land, and they continue in this role today. So if this is your first AdaptLA webinar, welcome. Thanks so much for joining, and we're really glad to have you. I'll just give a quick introduction to USCC Grant as a refresher to those of you who know our program and an introduction to those who may be new. So our Sea Grant program is a federal state university partnership that integrates research, education, and outreach with a specific focus on the urban ocean. So here at USCC Grant, our specific focus is that urban ocean and solving issues that arise out of managing people and natural resources in an intensely urban and developed coastline. So AdaptLA connects local coastal jurisdictions with the best available scientific tools and helps develop community of practice for the Los Angeles region's adaptation planning. So I'd like to introduce our speakers for today's webinar. I'm really excited to welcome Sarah Payne and Karina Alvarez. They were co-leads in the development of this C tool that you're going to hear about today. They were also co-authors on the paper written about this tool, which I think they'll share with you in their presentation, and we also have the link for that. So Sarah Payne is a graduate student researcher and a PhD candidate in the geography department at UC Santa Barbara. And Karina Alvarez is also a PhD candidate at the Julius Maximilians University of Würzburg. Some of you may actually recognize Karina from her previous role at USCC Grant, so we're really glad to have her back for our AdaptLA webinar. And I want to extend a huge thank you to both Sarah and Karina this morning for taking the time out of your busy schedule to come present this tool to us. So thanks so much, Karina and Sarah. And with that, I'll hand over the mic to you and I will stop sharing screen so you can go ahead and present.
Thanks so much for that intro, Rachel, and thanks for having me back after I defected, as it's been referred. But no, really happy to be here and really excited to see some familiar faces that I remember from my time at Sea Grant, and excited to share this tool that has been years in the making. With a lot of patience, a lot of generosity from coastal practitioners in Southern California, actually throughout the state. And so I want to say now, and I'll reiterate throughout this presentation that we're sharing this tool that we've developed, but we really want this to be an open conversation, and we want this to be something that is ideally helpful for all you practitioners. And so I hope that we can have a really good conversation after this demo in today's webinar, but also Sarah and I are always open to talk about how we can apply this tool for all of your needs. So like Rachel said, I'm a PhD candidate at the University of Würzburg, but also associated as a guest scientist at the German Aerospace Center over here in Munich. So today we'll be talking about how to use satellite remote sensing for bar-built estuary morphodynamic detection, specifically in the form of the C tool that Rachel briefly talked about. Oops. Okay. So we're going to just talk a little bit about satellite remote sensing. We won't get too technical because my understanding today is that there's a lot of practitioners, estuary coastal practitioners here today. So I'm going to focus on the other end where there might not be as much knowledge. And then we're going to talk about a little bit about the development of the tool, but mostly about a case study. So an example of how you might use the tool. And then we'll give a live demo so you can see actually the tool in practice. And then we hope to have a lot of time, like I mentioned before, for your questions and for discussion. So to start, what can satellites offer for bar-built estuary monitoring? First, this is preaching to the choir, I'm sure, but just in case, and if anybody's not familiar with the term bar-built estuary, these are estuaries that are seasonally closed and seasonally opened. And when they're closed, it's by a sandbar. And that opening and closure is largely dictated by complex interaction between marine and riverine forces. So it can be impacted by things like a storm, lots of precipitation, or huge waves or wave direction. And so they're really, really dynamic. And here we have an example of Malibu Lagoon, um, a beautiful barbell estuary at high tide or when it's full. But anybody that's visited the site knows that it can change in a matter of hours once the bar is opened. So for such dynamic systems, what can satellites do? First of all, the imagery that we'll be using today and in this tool is all freely available. So compared to in situ campaigns, it's a pretty sweet deal. There's a fairly short revisit time. So the satellites we'll be using have about 3 to 5 day revisits, which is a pretty good temporal resolution for data that is free. Another perk is that it's retrospective. So even if you decide today or if you decide in 3 years from now that you'd like to monitor a system, it's not too late to know what happened today or a year ago or 5 years ago. You can always access that data. And then, although the satellites that we're using today have only been launched within the past 10 years, they're planned to continue to be maintained in the long term. And so over time, you'll have these time series that can allow you to do more complex, maybe more interesting analyses on what's happening over the long term for these systems. It is important to also recognize some of the limitations that satellite remote sensing can bring. For one, the spatial resolution that we'll be talking about today is on the scale of 5 to 20 meters, mostly 10 meters, what we use. And so if you have an estuary that's really small with a really small mouth that has really fine scale breach events, satellites and this tool might not capture those changes. But for larger estuaries, it works fairly well. Temporal resolution of 3 to 5 days can be good for some phenomena, but for capturing, for example, what time of day did the breach event happen, or on what specific day did a breach happen, this satellite imagery won't give you those answers. And of course, clouds are a factor. We use a mix of optical, so like photograph looking images, and radar, which are independent of clouds. But the main source of this is in this tool is optical. And so those can't penetrate clouds. And so those days are then not usable. Here is a summary of or a really good visualization of what satellites can see over time. And so this is a 3 month time lapse of bar opening at Malibu Lagoon. And we see, first of all, this mouth really obviously open after being really, really thin, and on top of the inundation inside of the estuary being what looks like at capacity. The other thing that we notice is when the bar opens, the inundation extent inside the estuary changes really dramatically. So you see suddenly how much of the area is suddenly exposed or not covered with water. And so these two metrics, inundation and mouth state, are something that with these satellites, with this resolution, spatial and temporal resolution, we're able to detect. And that kind of led to the development of this tool. So the main capabilities of this tool, which we'll then show in the next 20 or so minutes that we have, is that you can get a time series of estuary mouth state. So for a time period for an estuary, when is it open? When is it closed? And you can get that for as long as the satellite is running. You also can get a time series of the estuary inundation extent. So how much water is there over time and how does that change? On top of that, you can visualize the specific capture. So you can inspect the images and play around with them and also get to do a little bit of comparison with what you think might actually be happening there. And then you can export all of these outputs for further analysis, visualization, so on and so forth. The main benefit of the tool is that there's no coding knowledge required. This was really important to us because there are similar tools that exist, but they are pretty coding intensive. And we had the feeling that a lot of practitioners just don't have the capacity or don't have the expertise for that. And so we wanted to make something that was really accessible. Um, on top of that, compared to other tools, this tool is really good at detecting very snake-like breaches or breaches that aren't necessarily just slicing the sandbar in a straight line. And then, like we just mentioned, you can visualize the individual time steps. And so it also allows a little bit of QA/QC on the user's end. So with that, I will pass it off to Sarah to talk about how the tool works more specifically and what kind of analysis or an example of analyses that could be conducted.
Thanks, Karina. Yeah, we'll hop into the methods of the C tool itself. So the original C tool had 5 different study sites we were looking at: Navarro, Russian River, Carmel, Ventura, and Malibu. But for the sake of this overview and in the paper, we primarily focus on Navarro and Russian River. Next slide, please. How we do the analysis starts with the satellite Sentinel-2 multispectral instrument, which has a 10-meter resolution for its pixels, about a 5-day revisit over the site. And for the Sentinel-2 multispectral imagery, we calculated the normalized difference water index. And all this is doing is it's looking at the difference between the green band of light and the near infrared band of light to try to determine what is water and what is not water. And that's the image that you see on the right. This is Navarro, and the blue areas have a high NDWI index, and those are most likely water. And the green and the white is either sand or land. Hopping into our next step.
Oh,
Thanks. Once we had the difference between what was water and what was land, we then focused in just on the estuary mouth. And what we did was we saw if within the estuary it was connected to pixels that were outside the estuary mouth. And so if it was connected, our analysis would return that it's a single object. The inside and the outside are all connected. If it was disconnected, it would be 2 separate objects. And this leads us to our next step of once we had, if the estuary mouth was open or closed, we would look at inundation within the estuary. And all we were doing there was we were counting the water pixels inside. Since we know every pixel is 10 meter by 10 meter, this can give us an area of inundation. And alongside using Sentinel-2 multispectral instrument, we also use that other satellite that Karina mentioned before, which was Sentinel-1 CSAR, and CSAR stands for C-band synthetic aperture radar. So this is a different type of satellite sensor. The main reason we incorporated it, though, is that it can see through the clouds and still capture a measurement. So it is really good at increasing the temporal resolution of our time series, but it's a little bit more noisy than Sentinel-2 multispectral instrument. So that is just a note that will pop up later that we did use those 2 different satellite sensors. Next slide, please. And here is an example of the C tool in action for Navarro River Estuary for February 2020. On the left, we have before with a closed mouth before the breach event. And on the right, we have after with an open mouth. Here on the first line of images, you see the Sentinel-2 multispectral instrument True Color. And True Color is essentially just what you would see if you were looking at it from an airplane. So that is the first line of analysis that we have here. So you can visually inspect with your eyes through our tool if you can see if it's open or closed. So that's a good way to double check that the tool itself is working appropriately. And on the bottom here, a line of images, we have the estuary mouth state analysis, where on the left it has 2 separate objects, and it's determined to be closed. On the right, it is fully connected as one object, and it's seen to be open. Next slide, please. Here we have the exact same event that we were talking about, but now we're focusing on inundation. That top line is that Sentinel-2 normalized difference water index turned into a binary. So essentially we took that -1 to 1 range of the normalized difference water index and determined a point where we thought everything above that point had to be water. And so that's what the blue you're seeing in the image is here. And then we just counted those numbers of pixels to see how inundated the estuary was. And on the bottom here is an example of the Sentinel-1 synthetic aperture radar working. And as you can see with the speckle, so that's that like salt and pepper effect in the image. It's a little bit harder to determine what is water and what is sand. But again, it has a higher temporal resolution that helps with getting a fuller picture of the time series that we're working with. Next slide, please. And here we're comparing this event to in situ water level data that we have. So on the bottom axis, we see a time series of February 7th when the estuary was closed, and then February 12th when it was opened. And you do see that drop in situ water level from that transition from closed to open. Next slide, please. And then we look at our inundation. So here in the yellow is that Sentinel-2 multispectral instrument, that primary sensor that I was focusing on in the methods. And as you can see, its time series is a little bit shorter and it doesn't change as much. But in the green, we have Sentinel-1 CSAR, which is capturing a little bit of an increase and then a decrease in inundation levels. And then finally, we have the black line, which is a 2-week combined running average of both of the satellites that we were using to try to get a better time series. And as you can see, it basically is following Sentinel-1 CSAR in this instance because it had that higher temporal resolution. Next slide, please. So now to discuss more about the CEA Tool's accuracy for both the mouth state analysis and the inundation. The accuracy of the CEA Tool's estuary mouth state analysis was compared to visual inspection. So just zooming in really closely on the image to see if the mouth state was open or closed. And for Russian River, we got percentage of 84%, Navarro at 80%, and then we also have this analysis for Carmel, Malibu, and Ventura. So we were feeling fairly confident in our estuary mouth state analysis that's produced from this tool. The inundation analysis, as you saw in these last couple of slides, should be taken with more of a grain of salt and should be compared with other data sets that are available. The 2-week running average generally correlated more closely with in situ water level data at Russian River and Navarro. But again, it is not as clear as estuary mouth state analysis for the tool. Next slide, please. And now this hops into the case study. So how might you use the tool to answer a question you're interested in? In the paper, we asked the question, how do barbell estuary mouth states vary seasonally? On the left, we have Navarro River estuary, and on the right, Russian River, with open in blue and closed in red. And on the y-axis is the count of recorded mouth states over the course of our time series. So as you can see with Navarro, the majority of instances, it does have a closed mouth state that was recorded, while in Russian River, it's the opposite of primarily having an open mouth state. There's also changes seasonally that are more evident at Navarro River estuary than we see in Russian River estuary. Next slide, please. And finally, this is looking at inundation extent, again, seasonally for each of the estuaries. The variability of inundation for Navarro River estuary was much higher in the fall and the summer than the winter and spring. And at Russian River estuary, we have more variability in the spring and the summer than the fall and the winter. Next slide, please. And this leads us to our case study conclusions of looking at Navarro and Russian River. Seasonally, Navarro exhibited more frequent closed mouth state observations compared to Russian River, and the inundation patterns varied between the estuaries and also between the seasons. As we saw in that previous graph, Navarro had the lowest inundation in summer with the highest in spring and the highest variation in fall, while Russian had the lowest inundation in summer, but the highest in fall and the highest variation in spring and summer. So our final takeaway was there's substantial seasonal differences between barbell estuaries, highlighting the importance of monitoring individual systems in particular. Next slide, please. And that I will pass it over to Karina to go into the demo of the tool itself.
Great, thanks, Sarah. So yeah, we wanted to make sure that we had enough time to actually show the tool and to be able to walk through some of the instances where the tool performs really well, and then things to keep in mind, some of the limitations that the tool experiences and how you as users can navigate that. So I am going to move over to the tool, but before I do that, I want to see everybody's faces. Can I get a raise of hands of who has a Google Earth Engine account, or you can just put it in the chat. Is there anybody that has a Google Earth Engine account? Okay, great. So not so many, but I'll go ahead and put the links in the chat so that you can play around and follow along. Um, okay, and then I'll go ahead and reshare my screen so that everyone can follow. Okay. So for those of you that have your account enabled, when you click on the tool link, it will ask if you want to add the code to your repository, and you just say yes, and then everything else should follow after that. Oops, I'm going to start from here. Okay, and as we do the demo, feel free to message Sarah at any point if you have any technical issues or need some emergent support, and Sarah will be able to support you. But otherwise, questions that occur to you for the discussion, you can save them, or I believe you can direct them to Dane, and then we'll get to them when we get to the discussion. Okay, so I will go ahead and get started. So for everybody, once you set up your accounts, if you decide to, you'll have the code here in the left in this scripts pane. And we'll explain all the other panes, but first what we're going to do is just press run. And so we can see what the actual tool looks like. Here we go. Okay, so here are the scripts. Here is all the code, which you do not need to look at and you can ignore. But because we want these two panels, we're gonna not collapse this totally away. So once you press run, you see that we have this interface that pops up. Here at the top is the user guide. It's a live link, and so that will be updated as we continue to improve the tool and to improve the guidance on how to use this. So what I'm going to do first is show one of our preloaded estuary examples, and then I'll show an example of, say you have an estuary you'd like to inspect, how you would do that. So as Sarah said, we did a study on 5 barbell estuaries in California, and those are all loaded in here already. So we have the dates, we'll leave those default, and then we have our areas. And I'm going to go ahead to the predefined estuary option. And then you see the 5 estuaries here. And I'm going to go to Malibu because we haven't seen too much of that one yet. And I would like to see both mouth state and inundation. And then you can go ahead and click on Generate Time Series. And I'm going to ignore customizations because for the predefined estuaries, that's not so important. Okay. So first thing we notice is that the map takes us right over to our study site. You can zoom in a little more. We see here the outputs of the tool. So we have Google Earth Engine language outputs, which you can also ignore, but later might be a little bit important. And then the main outputs that you want are going to be here on the left side for most users. So here we have this index that Sarah talked about that is important for most of the images that we'll be looking at. And I see that this is a pattern of opening and closure over the past or over this time period, but I want to look at 2 specific dates to illustrate some of the strengths and limitations of this tool. So first, I'm going to go to November 18th, and I can actually click on this. And then what happens on the map is that the most important layers automatically get loaded. So what we have here in our layer pane is we have a few things happening. So I'm going to dock it, or I'm going to make sure that it stays open so it doesn't keep hiding. And take all of them off so we can see what we have. here is the study area. We know where it is now, so I'm going to take that off. And then these three things can come up when you click on a date. So we first have the true color image. Like Sarah said, this is like if you're looking at a photograph from a plane, or you're looking out a plane window. And we can see that we have a bar intact. We see that we have fairly full inundation. And so we can go ahead and click on this index and see what that looks like. And just as we mentioned, the blue indicates likely water, green indicates likely dry. So in this case, sand or vegetation or something that is dry. And so we can see that it looks like it's pretty clear that the estuary is indeed closed. And then we click on the mouth state output, and I'll get rid of this so it's a little clearer. And we see that as per what we see in the visual imagery, there is a separation between the ocean water and then the estuary interior water. And so the tool therefore reads this as a closed estuary mouth. If we then go a day later, because it looks like it's really close to opening, or a few days later, so the next observation later, we see a few things. So looking at the true color imagery, it actually looks like there has been a breach, and that's further supported by the fact that it seems like there's a lot less inundation inside the estuary. We look at the NDWI, and that also seems to be the case. That seems to track. But then when we look at mouth state, it looks like maybe the threshold that we used was just either a little too low, which users would be able to change. But really what I'd say is happening here is that this opening is so fine and just on the cusp of this 10-meter resolution that it doesn't quite capture it. Now, when that happens, there is then the inundation that comes into play that you can use as I mentioned, as a kind of QA, QC. So for these same dates, the 18th and the 28th, I'm going to see what inundation looks like, the measurements look like. And so we have on this day, which is before the breach, pretty full, as we remember. And then just after, we see this huge drop, which, as practitioners know, indicates an opening. And we can see that that seems to track. And so we see here that one, we can capture these dynamics, at least visually fairly well. There is the limitation on the mouth opening size that may influence this output here, but that it can be, when taken in combination with the inundation reading or the inundation output, then practitioners kind of have a double read on what's happening and can combine that to look at the patterns over time. So I'm now going to switch to if you had your own estuary that you wanted to use. So when you want to use change the site that you're using, you're going to go ahead and reload the tool by clicking run again. And for those of you that have the account, I sent is also a link to a shapefile that, oops, I do not have it. Okay. Let me access that ever so quickly. Okay. I'm going to have to stop share for 1 second. Apologies. Okay. But for those of you that are playing along with the demo, go ahead and download that zip file, but you don't have to decompress it. Okay. Download and great. Okay, let's reshare. Okay. All right, can you all see this? So what I'm going to go ahead and do is navigate back to the tool. And I am going to go to this Assets tab. And I'd like to do a new shapefile, which is just the name for a file that has some geometry associated with it. And there are instructions in the user guide on how to create this so that it's compatible with the tool. So we see here that this is where we would add the files. We can either select them ourselves or just drop them in. So I'm going to drop this in here. And you see that there is a default path. It's not so important where the path is as long as you can find it later. So because I actually have this one already, I'm going to call this copy. But everything else you can leave as is. I'm going to press upload. And you see this loading over here. And this was the tasks tab was highlighted so that you can see that something is happening and that you'll be able to track progress if you open up this tab. So that's going to load for a minute. When it loads, you will have to refresh here on this side and then it'll pop up. But for the sake of time, I'm going to skip ahead and use the one that I already have. So if you recall, we had our start date. And this time, to make it a little more exciting, I'm going to change the dates and I'm going to do just a little bit more recent so we can see what's happening in the past few months, this site. For the area, I'm going to select my own asset. That's a little bigger so you can see. And then this is where you would put the sort of, think of it as a link to the data. And so what you do is you click on this asset, which is here. You're going to copy this table ID and then paste that right in. Okay. And again, I want to look at mouth state and inundation. And then from there, go ahead and generate your time series. Okay. So again, we get zoomed in on our site. We see this little highlighted, but I'll explain that in just a second. And then we see our layers, and I'm going to turn that off again. And this base map is kind of just a Google Maps reference, but it's not any of the data that is being processed in this tool. So we scroll down, we see that we have our readings of open and closed mouth state. And I want to show specifically, let's see, June 17th, because here's a really good example of one, how cool these systems are, but also just how the particular strength of this tool, which is for large estuaries with particularly dynamic mouths. So we see this is the true color image, again, what you see out of an airplane. This is that NDWI, the wetness measure. And then here we see the output of the open or closed. And we see that it follows this really neat snake-like pattern. So again, an example of the strength, but I'm going to show how to then customize the tool a little bit for some of the places that it might not be as strong. So if we look at August 26th, we see, first of all, that to our eyes, the estuary is really visually open. And when we look at the wetness index, it seems like that's the case. But what we also notice is that it really fades. This water is, for some reason or another, really difficult, really not showing as water in this measure. And so then when we look at the mouth state, it's coming up as these are separate objects. This water is not connected, and therefore the estuary is closed, which we as practitioners, or you all as practitioners, can tell is not the case. And so what we're going to do is we're going to scroll down to this customizations tab that we saw earlier, and we see that we have a few fields. So first we're going to look at this, and this is a field where you can specify the threshold that you want for your estuary. All these fields that we're going to look at are already set for the predefined estuaries, but they all have variable values for each one based on our analyses. We tried to optimize them the best we can. So I'm going to change this to 0.04, just very slightly down. And before I run the tool again, I want to check a few more things to customize. So we'll now look at the inundation graph, and this Sentinel-2 is using that true color imagery. And so we see that there are really, really low values, like here, that seem kind of impossibly low for what we know about this estuary. And when we look at the shape and where the water footprint seems to be, it kind of solidifies that this seems incorrect. And when we look at the true color image, we see that there are clouds. And so we know that value is not accurate. And we can even go as high as here. And I've played with this all day. So this is just an example of once you've played with it, how it can go. But it's really using just the kind of your local understanding of the site. And we look at this and we see that, again, there's clouds. This water should be connected there. There really is a lot more water in the site. And this, again, I've played with this all day. And so I'm going to use this as a threshold. I'll just go a little bit above because it seems like there's nothing else just above 137,000 meters. So I'm going to use that as the threshold. And what that does is it says for any image that is reading as less than this many square meters of water, throw that out. That's probably not accurate and it's not going to be helpful for our analysis. So we've customized this graph. And then the last place that we're going to customize is here. So this is where the Sentinel-1, the radar imagery would appear. Now it says that there's no features because essentially there's no data there. And that is because, and I'll try to keep this brief, but we have lots of backup slides to talk more about it. The way that the area is captured is at an angle from the satellite that's essentially shooting microwaves down to Earth. And anything that is closer to the satellite is in the near range. Anything that's further is the far range. And what we found is that anything closer to the satellite, or the images that are closer to the satellite, are much more accurate in their estimations of water extent than the far range for a host of physics reasons. And so the tool automatically only includes images that are in the near range. If your estuary just happens to not be in that range, then there's nothing that can be done. It's just where it lies. But the user can say, well, I want to just see what the far range looks like. I want to see what these slightly less accurate images look like, and then I'll decide if I want to include them. And so what you do is you change the angle. So near range means lower angle. And so we're going to go ahead and change the angle. And the way to do that is to refer to this console tab up here, and we're going to look for this max angle value. So here's our console. We scroll down. This is the error corresponding to the graph. And we see here is our max angle for input. So I'm going to change that to 42. Okay, now that everything has been put in, I can go ahead and regenerate my time series. And while I'm at it, I'm also going to clear the map. Okay. Now, what we see is our area inundated is a lot cleaner. It seems like the clouds are not having as much of an influence anymore. We see that the Sentinel-1 graph, so the radar data, is now generated. It's now including the far range images. And we see that there's something fun happening here, but this data is looking different. This chart is looking different because it's now incorporating both satellites into this time series. And for, like we saw before, for any of these single sensor graphs, these top three, you can go ahead and click on them and visualize the outputs, or of the outputs of the individual image. The last two things I'm going to talk about, and then we'll open this up for questions, are how to export the data. So we do all this analysis on the cloud and then try to make it as easy as possible to then play around with it yourself. So say for your estuary mouth state over time series, you want to have that in Excel. Click on that corner button, and then you can download that in any format that you'd like. So CSV, you can even have it just as an image. And you can change your window size, of course, to change how that image looks. You can do that for any of the graphs. And then you can also export the images in Google Drive as TIFFs, so as spatial data. Um, but you can pick any of the you can pick a host of products. So you can pick the true color, which is, as we mentioned, the red, green, blue. We can do the mouth state, so just focusing on what's happening at the mouth, or you can do the inundation from the optical imagery. This tool allows you to just export the first image in the date range, just because of Google Earth Engine strengths are in mass rather than exporting individual ones. But if you are really set on an individual image, then you can just change the range so that the first image corresponds to the range. And you'll go ahead and press export. And then we see again our task tab is open. We'll go ahead and press run on that tab. You can change the names of the task, which is not so important, but certainly of the file name. And then I myself know that I have a folder called C demo. And it just needs the folder name. It doesn't need the path, so it's really easy. Or you can leave it blank, as it said, and it'll go right in the main Google Drive. And then you'll leave it as a TIFF. And then you go ahead and press run. And you see that running here. But when I go here, it should at some point. All right, still running. And I think I'm running my computer at max capacity. But it will appear in this folder. So I won't wait for it to load because I know that we're a little bit, I don't want to cut our question and answer session short. So I'm going to go ahead and stop there and then stop sharing my screen and open the floor up for questions. Dane, any questions that you received during the
No
slide
questions.
presentation?
No questions yet.
Okay, cool.
Well, this is Ben.
I'll say that. Oh,
I'll
yes,
say
go ahead.
something. Well, I think you guys really added some great customized tools. Way to go. Look, really nice job on your presentation as well. Um, Nicely done.
Thanks, Ben. We have online for everybody else in the room, Ben Hull and Christine Lee, who are two of the JPL advisors that really led this project to where it is today. I do see one question
You
in the
guys
chat.
did that.
Teamwork. Okay, I see one question in the chat. It's very important. Thank you so much, Andrew, for asking. Can you say anything about the payment and subscriptions? The tool that we have does not have any paywall. It is using completely all the capacity that is free to use of Google Earth Engine. There is the little caveat that if your time series is really long, or if you're analyzing a huge estuary, you might run out of space. And it'll give you a message that say your memory is at capacity. And the workaround is just to do, a year at a time is usually no problem. And then you can piece those together in post-processing in your software or in your Excel or whatever that may be.
Yeah, thank you, Karina. And I also want to add that Dane has posted a couple times in the chat a link to the tool that's hosted on USC Sea Grant's main website. So on that link, we have the paper, we have the link to the tool that Karina shared, and a tutorial that or not a tutorial, but kind of a user guide that they wrote to use with the tool and kind of guide anybody's questions or kind of how to load everything up and things like that. So you kind of saw that today, but it's a more detailed guide that you can read. So we have all of that information posted on the USCC grant website. And Dane from ESA, I think you have a question.
Yeah. So I'm just curious, did you all talk to Tino Heimhuber at all when you were developing this? Because yeah, I see head nods. Yeah, he's developing the inlet tracker tool, and I'm sure there was some notes to be shared there. He was looking at similar stuff.
Yeah, and that tool is really awesome. We, in the paper, compare the outputs of our tool to the inlet tracker tool. And one of the main things that we found is that because they use a least cost pathfinding, these really sinuous or snake-like openings don't get captured. And so, again, that's where the strength of this tool comes in. And inlet tracker is a little bit more coding intensive, but it is really cool. And yeah, they've done a ton of awesome work on that. I don't know, Sarah, if you have another anything to add since you did the main comparison.
No, nothing really to add. I would definitely go check out that tool as well if you're interested in this topic. It's really amazing. We do have a more thorough comparison in our paper where we compare only the estuary mouth state analysis to inlet trackers analysis. And we run inlet tracker on their default mode settings for these different California estuaries. So that's not to say without some coding that inlet tracker could be improved in comparison with our tool. But yeah, great stuff. Definitely check it out.
All right. Well, unless anyone has any other questions, I think I'll go ahead and stop the recording. I don't know, Karina and Sarah, if you'd be willing to hang out for another 9 minutes or so. I'm sure everybody needs time to process what they've seen and maybe time to play around with the tools. So we can stay on for the remaining 9 minutes if anyone wants to poke around and ask Karina and Sarah any other questions while we still have them. Otherwise, I will send a follow-up email with all this information. All right, thank you, everyone. I'm going to stop the recording, but we will keep the Zoom open.